Yeah, I think that's good. Okay, everyone, welcome back. Let's get started. Today we're going to talk about communities and graphs, both kind of how to think about communities and graphs and how to find them. Before we get into the lecture, there's some kind of administrative stuff to talk about. Okay, so the last homework has been posted. We talked about this before. You should be able to kind of do the stuff for the last homework. I recommend trying to complete it before the interim test. Because we have kind of slack and ability to do so, I put the actual due date afterwards, but I recommend you try and complete it before. We won't be able to grade it before the interim test, but I think you'll be it'll be worth your time to do it as part of the practice and lead up to the interim. Okay, so I've posted a practice version of the interim test. You can find the link right here. Okay, I already opened it. It kind of roughly covers the topics that the interim test will be on: outliers and noise, streaming data, graphs, and dimensionality reduction. So I'm not sure. There are some of the questions I wrote so that they're kind of open-ended. I think it'll be good practice for you to take the practice interim test. I'm not sure if I will be able to post solutions for it. You're welcome to discuss them online. So Canvas, you're welcome to say, hey, here's a solution. I'm not sure about it, but I don't want to post them with the test. I hope you will go and try and take it without looking at any hints on the solutions first, and then if you have questions about it. But ones like this one are pretty open-ended. I'm not going to write down all the ways you could find outliers here. Again, the problems we ask here are not necessarily going to be the same questions that we ask on the actual interim, right? So you shouldn't expect this, but I think they should give you a good sense of it for practice. Enough people asked about that, and I felt I could do it. Yeah, so okay. That's one thing that's is coming up. Another thing is the final report is due on Wednesday this week, right? So that's coming up pretty soon. We talked about that kind of more in the previous lecture Wednesday last week. So I'm not going to go over everything, but again, 4 pages per member of the group. Don't make it too long. Please, if you're going to use all the pages you have available, hopefully it's full of charts and figures and stuff like that, right? You can have longer an appendix if you want to, probably won't get to reading it, right? It's great if you did a bunch of this stuff, but kind of even with a large project, there's a skill in writing stuff with so brevity, pulling out the most the most important pieces for that. Okay, one thing I do want to talk a little bit more about is the poster outline. Your poster outline is due on the Monday. Let's see, when's the poster outline has a couple of deadlines. let's see, let's look at the guidelines for the poster. Okay, the project. Okay, so you will present the poster on April 30th. This is the day of your final. Okay, so the poster presentation is your final in the course. But you need to turn in a kind of a outline of the poster on April 21st. Okay, so you need to send in a draft, and then TA Elham and myself, if needed, will look over and may give you some feedback of stuff to change. I don't just want you have you do a poster. We're going to try and give you some guidance on how to do a poster. So if you hit it right the first time, looking at examples up here, that's great. Or from instruction class. If not, we'll give you some feedback. I'd like the posters to be really great. The poster day is a lot of fun. You get to show off your stuff to other people. If your poster looks kind of subpar to everyone's else, you'll wish you had done a bit more. Elham posted this guidelines for poster. Again, we will print the posters for you once they've been approved. There was a small fee that went with this class that goes towards printing the posters. So we will handle that for you. Then on the day of the poster session, they will all be there with easels in kind of the hallways of like the Merrill Engineering Building. And we will be there to have the poster session. The dimensions can be 3 feet by 2 feet or 2 feet by 3 feet. You can have them long and tall or so wide. And then there's some guidelines on here. So there will be a poster session for help that will be on, I believe it's going to be on the 21st in the afternoon. So Monday, let's see. So it should be Monday the 21st I think it's, is that when I schedule it? In the afternoon after class after the test on the 21st, you can go and do like a poster session and kind of review what you've done so far and get some feedback on how to improve your poster, share it with other people in the class. And so we're working on booking a room. I think it's going to be it'll be in the Merrill Engineering Building again in this 3147. I'll post this online. Yeah, so okay. So if you want to see more examples of posters, you can come and see some after class. Before, I just want to say, in general, you kind of want, kind of as some general thing about a poster, you often want to think about it as a single big canvas. And remember to have a title across and then the names of kind of the names of the people on the poster on the top. You want to be able to easily find posters should quickly tell you about what the whole thing is about. And then I like to think of it if you have a wide poster that's 3 feet wide by 2 feet tall, then it's common to think of building into 3 columns, right? And then you can have you want to have kind of a big kind of chart, often in kind of the top of the middle column or someplace in the middle that catches everyone's attention of what is the cool thing that you're doing, right? Some big thing or graphic. And then you also kind of generally want to think about it as having these 3 columns, and they're kind of read in order on the chart. So you read the first column, then the second column, then third column, but you again want to have a big thing that's kind of catching everyone's attention in the middle of the poster. Okay, and you often want to have something like the kind of the intro, the motivation over here. Maybe you have a problem statement down here. Okay, then the second column, this part is this is what you did, right? Is kind of the middle of the poster, the cool thing that you did. If there's a key idea that you want to talk about here, and then this is often the results. Okay, so it could be, and what you did and what the results are, maybe these are mixed up in some way, but you want to say, okay, here's the evaluation, and then maybe here's a discussion, conclusion. Okay, or if you need references or thanks, they can go down there, right? So the coolest part, the middle thing that you did is right, front, and center. Okay, and the idea of having it in the 3 columns allows you to tell a story. If you do it vertical, it could go left to right in 3 pieces, something like that. But the idea is you're telling a story with the poster. And so there are 2 main types of posters that kind of people make in kind of these research posters. One type of poster is there's a couple on the wall outside that are meant to be put on the wall and left there, and you walk away from them, and the poster is kind of like a paper itself, has lots of text on it, and all the explanations are on there, and you don't need someone there to help you out, kind of explain it. That's not what we're doing here. Okay, these are posters that are meant to facilitate you explaining your project to someone else who's curious and to do it efficiently. So if you want to explain the project to someone and you have some cool visual aids or a chart or kind of explanation of what you did that would be really useful to explain that to someone, that should definitely go on the poster. Okay, so those are the things you want to be there and be able to quickly explain to someone what's going on. There are going to be 2 main types of people you're going to be, or maybe 3 main types of people who you're going to be interacting with on the poster session. One is random other people in the class walking by. You want to catch their attention so they come in for more. Okay. 2, you're going to have me. I'm going to come around and look at all the posters, and I'm going to have to visit 41 posters in the time. And okay, I'll try and start a little bit early if some of you get there early, and it might go a little bit late, but I'm going to have realistically like 2 or 3 minutes per poster. So you need to convey what you did, what was the cool idea, and what were the results and conclusion from it in 2 to 3 minutes to me. And I want to have some of that time so I can ask you some questions. Okay, so I'm going to have a crazy day to go through and interact with all the posters. Has to be really quick. Posters should be able to convey that. There are going to be other people, your peers, coming up to you to ask you about your project because you made it seem so cool and because it was so cool, and you want to be able to go more in depth with your peers. And this conversation will be in the 5 to 10 minute range. Okay, you want to be able to go more in depth for some people than with other and explain to them, oh, how did I make this decision? Oh, we tried these different things. Oh, this worked really well. This one didn't work really well. And they're going to go in and be able to interact with them and zoom in on certain details, right? So those are the kind of the perspectives you want to bring into this poster. Yeah. So how many of you have made posters for something like this before? Okay, and how many haven't made posters before? Oh, okay. For those who made posters, where did you make them before? Just in your job research?
It's like undergraduate research, UROP for.
Oh, okay, cool. Yeah. So UROP, right? So if you're involved in undergrad research, you'll be making kind of posters like this. Yeah. So and you enjoyed going to see other people's posters and stuff before?
Yeah, right.
Yeah. Okay, cool. If you haven't been to a poster session like this before where you're invested, it's going to be a lot of fun. So it's great. Any questions on this? Again, the outline will be due on April 21st, right? And then we'll give you feedback as needed. Not all of them will need feedback, and then if you need to adjust it, you have a few more days to adjust it, and then we'll print them before the actual kind of poster session, which should be the final. Great. So, okay. Okay, we're talking today about communities in so graphs, and this can mean a lot of things, and often the examples often come from ideas of social networks. Okay, and I mean this in a fairly general sense. Okay, and again, we're talking about graphs, right? And so a graph, remember, is a bunch of vertices. In a social network, these would often be people, but they could be companies or brands, and a set of edges, which are representing how these things are connected to each other, right? So if you have a set of these vertices, okay, and then these edges will be connecting between these, okay, these vertices. And so we'll think of, again, these as being people or entities. Could think of them as web pages in the web graph, but in social networks, often you can have like a company page or kind of a university page, right? You're trying to advertise something. And these edges, these are the connections between people. Okay, and they're often measured as will often model as binary. Okay, and this has always seemed kind of based on some of the philosophical stuff or philosophical view I bring to the rest of this class. This always seems odd to me that we've represented an edge, a connection as always being there or not. But these choice of edges is really going to be a modeling choice. Okay, are these things connected or are these not connected? Okay, so kind of a common idea is these could be accounts on like Facebook or Twitter, right? So if you're on Facebook, right, there are two kind of maybe obvious ways of maybe having an edge. So say Facebook, you could say if there's an edge if you're friends with someone, but I never got on Facebook, for better or worse. But I believe there's a limit of the number of friends any person can have. It's like 2,000 or 5,000, something like that. So, and there can also be like a relationship of like if someone's following someone else. Okay, so can be a cap on friends. This one might be less than 2,000, but the number of followers someone can have can potentially be much larger. I think I was reading like Ronaldo has the most followers on Facebook, and it's around 200 million. It's like under 200 million, 170 million. The next after Ronaldo is like the company page for Samsung, I guess. And the number 4 person was Mr. Bean, apparently, which was surprising for me. So how do you choose whether to put an edge on these graphs, these social network graphs? We had talked before about building graphs by having a similarity between objects, and then you look if the similarity is above a threshold. You can do this if you have a notion of similarity, but this seems kind of requires more modeling. For graphs, you kind of really would like it to be discrete. Okay, whether the edge is there or not. And a lot of large-scale graph analysis deals with this discrete nature of the edges. It's either there or it's not there. And so how do we choose this is not kind of an obvious answer. But okay, so we're going to try and kind of work with graphs where we're given a set of vertices and a set of edges between them. Again, sometimes I'll talk about directed edges, sometimes undirected edges, okay? And you know, in many cases, the differences between if you have directed edges, if you make it undirected, so you can assume you can move both ways, the results look kind of fairly similar in most cases. Sometimes there's some differences work, but it's not a huge complete difference in the techniques used. But kind of the way we modeled Markov chains, how do you set up the initial probability transition matrix? You might have kind of directed edges or undirected edges, but ultimately you get some sort of kind of graph or matrix that you work with. All right, so how did the work on these social networks start with? Okay, so early kind of social networks. This was very exciting from like a sociological point of view, is that they drew a lot from sociology. And so this is kind of a field of how people interact. And so what they meant by a like social network was that there was a graph of often people, and these were kind of some interactions between the people. Okay, so these red were interaction between people, right? And these blue nodes were people. And now we have kind of Facebook and Twitter and WeChat, and there's all these ways that we can kind of measure how people are interacting, kind of this automated way. It's part of the zeitgeist of these big companies. How do you think that they study these social networks and interactions pre like these social networking apps on the internet? So how do you think they would do these kind of studies? Yeah. Yeah. So there'd be a questionnaire. So how would they collect a questionnaire, right? It's just the people in the class, or? Yeah, so they would go and they would have questionnaires. And so it'd be kind of common to kind of go into a middle school or go into a high school, and go and try and give questionnaires to everyone and ask them who are their friends, who's their best friend, who's in their like friends groups. And this was like a manual process. Okay, it was very time consuming, right? So the size, the number of vertices, right? The number of vertices here would be on the order. A lot of the networks that were studied were like 100 to like 200 people. Okay, and so they would try and study these networks, and occasionally, not rarely, but occasionally they would go and they would measure this multiple time and try and understand how this changed. They'd go back into the same high school and ask people again, okay, who are your best friends with? And if it was different than before, then they would update and try and understand the dynamics of these like interactions. All right, and so there are some old data sets on the web which have been heavily studied, like Zachary's Karate Club is a really old kind of data set on there. It's like 100 nodes in it. And this was kind of like what the data was like before these like social networks. What was kind of nice about them, and so I'm old enough to remember a little bit having friends who tried to create like who was friends or who had dated who, and you can often draw these graphs. They're often planar or close to planar. So planar means you can draw the graph on the plane, or technically on a sphere, with but no edges would cross when you did that. Okay, so you could draw them and kind of visualize all of these connections here. Okay, and maybe there might be a few connected edges, but if you're careful with drawing it, you could really see everything by just drawing the picture. Okay, when the number of vertices gets much bigger, right? There are kind of like hundreds of millions of people on Facebook and Twitter and these other social networks, you can't really draw pictures the same way. So we needed, so both we able to start seeing things at much larger scale, but it's much harder to do the analysis of these things because the scale meant we couldn't just draw pictures. All right, so this was around kind of the 1990s, early 2000s. This was kind of the view of things, except there's another view. There was also kind of the mathematical models of graphs, okay? And so there's this night the mathematics that was developed, and they mostly worked around what was called an Erdos-Renyi graph model. And so this could scale up to, with the number of nodes was kind of greater or equal to 1,000. And this particular model said that they would have n was the number of nodes, and we would have a value p, which was going to be a probability, so it's n01, and this was the probability any pair of vertices had an edge. So what's the probability any pair of vertices had an edge, and what was key about this is this was independent. Okay, they studied this under where their probability of an edge between two vertices was independent. And then there's a lot of cool mathematics that happens. And so you get a very large set of these kind of these vertices you can deal with and try and study what happened. And then they would say, let's see, gradually increase the value p, right? And what happens is, as you increase the value p, you kind of get more and more connections, and these are kind of random connections. And there was actually structure that emerged. At a certain point, you would start to see the emergence in the middle of some kind of shape, which was like, which is often called like a hairball. Okay, where there's a central node that was strongly connected, or where everything could get to everything else pretty quickly. You could get from one node to any other node in a small number of hops. And then there would be a small number of these vertices that are connected to the central kind of cluster in the middle by just one edge, and they're off by themselves. Okay, and so this picture, what I've drawn here in the bottom, is fairly representative of what these graphs look like. There's one part in the middle where you can't see what's going on because it's got edges going every which way. And then there are a few edges that have or vertices that have only one edge that are coming out. And maybe a few vertices that don't have any edges at some point, depending on what the probability is. Right? Once the probability gets high enough, everything is connected, and everything is kind of connected to multiple things. And you could study this kind of these phenomena. And again, around 2000, there's a rich mathematics around this of large graphs. And so what people knew at the time, before we started collecting these social networks, is either, okay, it's some study of these small graphs on the order of 1 to 200, because it was a big manual process to collect all these surveys and draw these pictures, or it was these random graphs, more or less. And it was mostly this simple model of random graphs, that had every edge be independently connected to every pair of vertices independently connected with some probability. This we could study, and we had a pretty good understanding of this. Okay, and then we started seeing these actual large sort of social networks graph, and they didn't look like either of them. Okay, things were very different. It was not so planar and simple. The sort of structures we thought were here, well, they didn't quite look the same at larger scale. And when this is what we knew about larger scale, there's one hairball in the middle, and then a bunch of a few stray edges, and this is not what the graphs look like either. There wasn't just this one big kind of randomly connected kind of dense region in the like in the middle earlier. Okay, so it was kind of something different. Okay, and here's an example of a sort of question that that kind of we could start to ask. Okay, so let's say we have a graph here. Okay, so I'm going to say that these nodes are going to be in a community, and this is a labeled ahead of time. Think of this as a bunch of people as part of a social network, a part of a big social graph. They have labeled they're part of a group. This could be a group made by Facebook to discuss a certain topic. Could be they're part of a church group. It could be they're all on a sports team together. It could be they're all in the same class together, right? Okay, this is a labeled group where I know people have this, people have this label. And, okay, now I've got two additional people, Y and X, okay? And I know these people have connections to people inside of this group. Okay, in fact, they both have 3 edges into people in the group. Okay. Okay, but the structure of those 3 edges is different. Okay, and I can ask of these 2 choices, who is more likely to join the group? Okay, X or Y? Okay, now the structural difference I wanted to look at here is that X's they both have 3 friends into the group by those 3 edges, but they haven't officially joined the group yet. X's 3 edges are all friends with each other, where Y's 3 edges, they all have other friends in the group, but they're not kind of friends with each other. There are no edges in between these here, right? There's no edges connecting those cases in Y. Okay, and there were kind of, before we could collect real data on large scale groups, we couldn't really answer this question. Who is more likely to join the group? Okay, so X has a bunch of similar support. If they join the group, they're joining a tight-knit friend group inside. Kind of a bunch of people they know, they can interact all together at once. Or Y would have some independent support. 3 different parts of the group were all friends with Y, so they have 3 kind of different reasons to join. Okay, and so it was not clear which of X or Y was more likely to join. All right, so what do you think? Who's more likely to join? Any thoughts before we vote? Yeah.
Yeah, I'm gonna say X because, like we see here, the connections that X has are also connected to other, which I guess we need, if once that community is expanded to include X, there's more connectivity between them. This makes a stronger community, quote unquote.
Yeah, great. Okay, anyone want to make the argument on the other side for Y? Yep.
So if that's a weak connection, then maybe the probability of being out there is super great. Whereas Y has like access to like 3 different subgroups that might have varying supports to larger ones.
Yeah, great. So this is kind of a very different view. The independent support versus the 3 kind of a tight kind of community inside. Any other points of view on this? Okay, Let's vote now. Who thinks X is more likely to join? Who thinks Y is more likely to join? Yeah, okay, we have a little bit more votes for X, but this was kind of the state of things in around 2000. We didn't know really the answer. Both of these arguments were put out there, but they were just theories. They weren't able to test them until we could do this, and the answer turned out to be X. Okay, so that having a tighter knit kind of group of friends all together was more likely to make you join a group. All right, so this was really in this kind of understanding of group dynamics has been really important for the social network companies for a variety of reasons. One I'll talk about is the model of graphs. I'll talk about that next. The other reason is this kind of also worked inversely, is that someone is less likely to leave a group if they have kind of a really tight connection inside there where they have kind of a strong with multiple kind of people they know who all know each other, as opposed to this case. So they would so social network companies wanted to form these types of edges, they determined, as not necessarily these types of edges. If they can advertise, if you're on a social network, they'll say, hey, would you like to also be friends with this person, right? They'll try and make these suggestions, and they would like it to be this type because this is more likely to keep you engaged, allow you to have these joint conversations. And there's this was true in the early 2000s that they kind of, in like the dot-com boom, which is when I was going to college, even these companies, which a lot of them went so bankrupt, it was very clear to them that they wanted to build strong communities and get people hooked. They felt if we can spend a lot of venture capitalist money, which still exists today, to build up a community, then they'll be hooked to it and they won't want to leave. And then we can, increase the price or increase the number of ads, and they will probably still stick around. They'll have momentum there. A lot of the social networks now, Twitter and Facebook, you'd say, I bet we could do something better, maybe, but there's a lot of momentum there because you don't just know 3 different people, but you have a really community that if one person left, they're going to feel like they're losing their kind of really tight friend group because that's how they are interacting with these people. So there's a lot of effort to build these sort of tight connections inside these sort of social networks. Okay, so this kind of realization was kind of quite important here. Great. Okay, this also led to, as I mentioned, there were these kind of 2 types of graphs. One was this near planar graph you could draw that were really small, and then there's this random graph model, Erdos-Renyi model. But this kind of led to other models of what graphs looked like, because we wanted to study them at scale. And sometimes we could get some, if you were not inside one of these companies, they for a while they were posting their social network graphs online, but they stopped doing that because of some privacy concerns. And so if people in academia wanted to study and come up with a theory of these graphs, what would they look like? How would you find communities, which we'll talk about soon? And what was the what is the structure of the graph? It wasn't this hairball. That's not what the big graphs we saw on social networks. That's not what they looked like. And they weren't planar. We couldn't draw them either. So what is a model for generating random graphs so we could simulate the data and then study a whole bunch of variants under the simulated data that look like it matched the real data. Okay, and so this is still somewhat of an ongoing question. We don't quite have the perfect model for what these graphs actually look like, but there's kind of one theme which I will talk about called preferential attachment, which is kind of a consistent part of it. And then there are some nuances under the hood of what other things look like. So let me start with this. This is the idea of how do graphs form. And the idea is you have a set of nodes, okay? And there are some existing edges, okay? And now I want to propose to kind of this person here, I want to propose to them a particular friend that's likely to succeed. Okay, that's likely to actually form an edge. And one, I want a graph that's more tightly connected, but also I want to know which one is more likely to be successful in actually joining. So if I didn't, even if I did nothing, I just created the network and I just let it go and made it useful, what sort of edges would I see? What I tend to get, I have A, B, and C, and D. Okay, so if I'm at node C here, am I more likely to see a new edge with B or a new edge with D? And there exist edges between A and B also. Okay, and so this is independent, again, of what the network is trying to do to try and promote these tightly knit groups, but it's more likely, so this edge is more likely to form. Okay, so if C is connected to B already through a joint neighbor A, they're more likely to form an edge with B. Okay, the idea is that I'm more likely to form edge A, or call this CB than CD if it forms a triangle A, B, C. Okay, a triangle is what happens here. This is a triangle. Okay, you probably know what a triangle is. It's a shape with 3 vertices and 3 edges, right? But it's in a graph, we call it triangle if it's basically 3 vertices that have all pairs of edges, right? In this case, it's only 3 edges. So it's okay. And so this structure, the triangle structure in graph, it turns out to be very important. You're likely to form these triangles. You're more likely to form a new edge to something that will complete a triangle than something that will not complete a triangle. And maybe you might actually have multiple A prime, which is also friends with C and B. If there are multiple triangles that will complete, it's even more likely to form. Okay, so the more kind of triangles that will complete, the more likely it is to form. Okay, and so this is something that can empirically was found fairly clearly in the early 2000s as they were studying the formations of these social networks. And then you can also generate graphs in this way. You can generate graph by starting with some random edges and then trying to more likely add an edge if it will create a triangle. So I can somehow change the probability of the random edges dynamically as the graph is being formed. Okay, and so if you generate graphs this way, I throw down all the vertices and then I add kind of edges ongoing, and I'm more likely to add ones that are forming these triangles. Well, then these graphs look a lot more similar to the graphs that you actually see formed. Okay, they have some, still you can say, you can do some simple statistics like what is the average degree of a node, but so the degree would be how many edges does a degree have. So the average person on Facebook has like 200 roughly friends, and then similarly on Twitter, around 200 roughly kind of people they're following or also following them, right? And then there are some people who have more than 200. Who is more than okay, so who's on Facebook and active? No one. Okay, who's on Twitter? A few people. Okay, I'm okay. And then what social networks are you on? I have no idea. I'm old at this point. Yeah. So Instagram, great. Who's on Instagram? Someone. Okay, great. Okay, so how many? Who has of those on Instagram? Who has more than 200 followers and less than 200 followers? Okay. So Who has more than 1,000? So who has more than 10,000 followers? Okay. Okay, great. Instagram was not one I looked up. Okay, so Instagram is now what all the cool people are doing, I guess. You know. All right. So but the same thing happens. There's a degree distribution. On average, people have around 200, maybe more than that. But then I guess I'm also on Instagram, but I follow like one person. So there are also people like me who don't follow anyone. There are also these, but then there are some accounts that have a huge number of followers, right? Like on Twitter, Elon Musk apparently has over 200 million followers. Maybe 40% of those at least are bots or something, but still it's a pretty large number, right? So you have to kind of, there's this degree distribution that varies differently. It's not like it's random and near uniform. And when you look at the preferential attachment model, you can set the probabilities of this attachment, right? So that it actually mirrors kind of what the degree distribution is of these large graphs, right? And to some extent, it has certain clumps and clusters in it as well, because it will tend to form things that have a bunch of kind of similar edges, and it will make those regions of the graph so more clustered, right? So you tend to have these cliques within the, not exactly cliques, but these groupings and communities within the graphs to some degree. Okay, the amount of communities and groups of the graph with just building the preferential attachment model is maybe not as strong as we actually see in practice, but it's kind of an first time important step in the evolution of these models. Okay. Okay, so this kind of gives us a sense of how would we model the randomness in these graphs. But it hasn't quite, and so far I told you about this challenge of, if we have a community, how do we think of this growing? But I haven't talked yet about, and so kind of the second half of this lecture will be, how do we find communities? How do we find or define communities in graphs, right? Yeah, so, okay. So what we've actually already seen some really important tools of how to do this so far. Okay, so one thing we talked about was spectral clustering. Okay, so spectral clustering, remember, was a way to kind of find look at the normalized Laplacian of the graph, and this turned it into where we projected down all the vertices into a one or multi-dimensional space using the eigenvectors of that, and then we cluster, right? So this is a clustering, and so for the most part, this decomposes vertices into disjoint kind of both sets, right? So it's decomposing the graph. Okay, so this is not necessarily the same thing as communities. It might be a good starting point. But if I have a graph, and again, it's a little bit hard to really explain this on a small scale, but you could think of having two subgraphs here, right? These two pieces, but there might actually be a third community that's overlapping with both of these, right? So there might be three communities here, 1, 2, and 3, and they are like overlapping, right? So you can be in a church group and you can also be on a sports team, and they don't have to be the same thing, and you can be involved in both of these communities at the same time. And typically, people have like their work or school as one kind of social network, their home and family as another, and then maybe they have a third one that they have some hobby, right? And these can be overlapping with each other, and they don't need to be or disjoint. But the spectral clustering kind of gave us a first mechanism to kind of decompose the graph into pieces that were tightly connected. Again, we want to retain, if things are going to be more close, if they have more edges with each other, they're more similar. And so we're going to kind of retain things which are kind of tightly connected with edges. The edges tell them that these vertices should be grouped together in some way. All right, so this is one way of thinking about it, but it's more restrictive than if we wanted to just find communities. So communities, they can overlap, and not all vertices must be in one or more. So you can have some vertices not in like any communities, right? So if you have some bots, maybe there's a community of bots out there that aren't real kind of users. But those, if they're just one node, not connected or following anything, it doesn't need to be forced into a community either. You want to find kind of a tight set of nodes, and it's okay if these overlap, and you don't need to classify things that don't need to be pushed in. Okay, so this is kind of the spectral clustering gave us a good place to start. We want to somehow think of finding these regions which are tightly connected. Okay, so we want this to be a tightly connected subset of vertices. Okay, and so for two vertices, V and V prime inside of a community, then I would say the probability that V prime is in the edge set is going to be high. Okay, so that the probability that if two vertices in the community, the probability there's going to be an edge, we think of that as being high in some sense. That's how you think of a community. What does high mean? How do you calibrate this? This is kind of various kind of there are various ways of thinking about this. Okay, let me start with a top-down way of thinking about this, called betweenness. Okay, and this will be betweenness centrality, sometimes it's called, and this will be a top-down view. Okay, and the idea is we have a graph that will look where it's going to look something like this, and we can think of this kind of conceptually here as this as being so county, and this region up here being so like Park City, right? And then you have like an edge here. This would be like like the part of I-80 going up, so Parley's Canyon, right? Write that better. So there are these kind of two connected regions. This would be like a road network, And then maybe there's only one road. I guess there are other ways you can get up there, at least in the summer, that can connect these two communities. Well, then if I can identify the communities by chopping this edge, I want to chop, this edge, and then what's left after I got rid of a really highly connected edge, what's left, the connected components, are the communities afterwards. Okay, and betweenness gives a way of quantifying how important is this edge, right? So again, the goal is to remove these highly connecting edges, and then the remaining connected components are communities. Okay, and so this particular way of defining it, called betweenness centrality. So the betweenness of A and B, this is going to be the fraction of all shortest paths on kind of the graph GBE that use edge AB. Okay, so the fraction of all the shortest path edges that use this edge AB here. So I can, again, think of this as node A, and this is node B, right? So if I want to take a shortest path that somehow ran from this node to this node here, it basically has to go through this one edge. Almost all, if I start with a vertex on the left and a vertex on the right, and I want to find the shortest path between them, well, I might use different vertices in between, but I basically need to use this one edge which is connecting. There might be this other way to get from Salt Lake City to Park City. I guess I can go up to Ogden and then around, this way, perhaps, but that would not be the shortest path. So there's a lot of vertices here and a lot of vertices in the right part, the Park City part, and so all the shortest paths must go through this this interstate here. So in parlays, so then there aren't a lot of ways to get between them. So if I can identify these high betweenness score edges and remove them, I gradually think of removing these edges in the reverse order of their betweenness score from the highest to the lowest. And then if I stop at some point and I say, what are the connected components of the graph? Those are my communities. Again, this is like a partition. I might have some vertices not connected to anything. So it doesn't require that. If I go to a fairly low betweenness score, I'm only going to get these fairly kind of these communities that are kind of fairly evenly spread out between themselves and not anything in between, right? So if, in particular, if I were to add a vertex in the middle here, it's not really going to change that the shortest path still needs to go in parlays, but that vertex in the middle may not be in either of the communities. Okay, so for road networks and stuff, this works pretty well to identify kind of clusters of streets and stuff. Okay, so this betweenness centrality is just one way of quantifying how important like one of these edges is. Okay, there's something else we studied already which could give a similar notion of importance like this that can be used basically for the same strategy of finding the things with high importance and remove those. Once I've removed those, then the connected components left over are going to be the things that are the communities. and that's this strategy here. So remove highly connecting edges or elements, and remaining connected components are the communities. What else have we used that could be used directly in the same strategy that we talked about?
We talked about like modularity cuts where each component has like a density to it. Call it off based on like.
Yeah, so doing normalized cuts within spectral clustering was trying to do something fairly similar. But it wasn't, the cut itself was not a score on individual vertices or the edges in this case. It was trying to say a score on a collection of edges I would cut all at once. That I would make the kind of the vertices into these disjoint parts, and then I would have a score of things going across there. So it's kind of a similar strategy, but as graphs get more complicated, there usually is not just one edge in the middle, there are multiple edges, and then how once you define the cut, you're really doing something like, it leads you to the spectral clustering algorithm, which is again a top-down thing, but it's not individually scoring elements. It's scoring these cuts kind of more generally. So it's a good strategy for this thing, but it's not what I'm looking for here. Yep.
If the edge A is angles, it probably has a low.
Okay, yeah. So one thing with triangles is, yeah, I could count the clustering coefficient. So I can, I'll mention this. Because this is something you brought up. The clustering coefficient is basically so you often define this for a vertex. So for a vertex VI in some set of vertices, the clustering coefficient, we'll call it CI, is going to be equal to 2 times the edges actually I can find this for an edge. Let me do that instead. Okay, define this for an edge. Okay, it's going to be 2 times the so this edge EI is going to be V prime. The degree of V plus the degree of V prime. Okay. So it's no, it's slightly different than this. Hold on. It's okay, it's the define the neighborhood of this as the edges that include VI. Okay, so if I have 2 vertices V and say V prime, I've got a bunch okay, its neighborhood is so this would be the red ones would be the neighborhood of V prime, and the orange ones would be the neighborhood of V. Okay, so this would be the neighborhood of V. And so I'm going to look at the so if I have, again, I'm considering this edge here, okay, between V and V prime, then this is going to be the number of can write it as the intersection neighborhood of V intersect the neighborhood of V prime. The size of this divided by the degree of V times the degree of V prime minus 1. Okay, I'm not sure I got this quite right as I'm redefining this on the fly here, but it's something like the number of shared things in the neighborhood between the two vertices. So kind of the number of triangles over something like the expected. This is proportional to the expected number of triangles. And this is 2 times the number of triangles. Okay, so kind of the number of triangles over the expected number of triangles. So if I basically count the number of triangles, but I want to normalize by the degree of the 2 vertices. So if I'm friends with Taylor Swift on Instagram, right? You know, then she's going to have a lot of edges, and so I may not have as many edges, but I want this to be proportional to the number of possible kind of friends that we both have. So that would be how the clustering coefficient of this edge. It would be a really strong edge if it has a large number of shared triangles proportional to kind of the expected number of shared triangles. Okay, this is called the clustering coefficient. And this is kind of like what you said, this is scoring an edge based on how many triangles it's part of. But it's typically done relative to the degrees of the vertices, because otherwise, you know, it's not fair because then you would just by being friends with Taylor Swift, there are lots of people who might be friends with her. So there'd be a lot of triangles there, but maybe not proportional to the number of degrees of that vertex. So I could use clustering coefficient for this reason as well. Yeah. So that would allow me to score all of the edges and then again do a cut in between this. So now I want to cut things that have a low clustering coefficient, right? So I would look at the edges that have a low clustering coefficient and remove these. And then what's left is going to be a tighter community. Okay, what things that have a lower clustering coefficient? So these kind of a low clustering coefficient. These are these good cuts. Okay, that's for true. That could be 2 vertices that maybe have an edge and both have really high degree, but don't have any shared triangles. That would be a good thing to cut. But it's also going to be kind of vertices with or not vertices, edges with low degree vertices, right? If the numerator, the number of shared things in the neighborhood is going to be 0 if a vertex is not connected to anything else. Okay, so this is this is also going to prune off these singleton things in the graph. So if I have a road network that also has kind of some edges out here, it's going to cut off these edges and leave really the core part while also cutting kind of the things on 80. So we'll first probably cut off all these stray edges. And so it's kind of a different flavor, right? So you could use these two different methods, betweenness, centrality, and clustering coefficient, and you get kind of very different senses of the communities. Okay, this is not necessarily in a lot of shortest paths, so it may not be in betweenness centrality, but it would have a low clustering coefficient, so it would get pruned first from there. Okay, that's a good point. There's one other thing I wanted to mention here. We could also use, or I can use, so I can use the score, this score for page rank, as well to score the importance of things. We talked about page rank on the vertices. How important is a vertex to the graph in terms of it's a really important hub. A lot of things are connected to it. The page rank score for these green vertices is probably going to be pretty high. I have to go through them to get this connection. If I want to go back and forth between these two parts of the graph, I have to go through these nodes. If I remove these nodes, okay, I've left the graph fairly well clustered with these communities. Okay. The red node might be its own community afterwards. It may not have as high of a PageRank score as the green ones. Okay, but anything going across would have to go through the green nodes. I can also invert this and kind of run PageRank on the edges instead of the vertices, where the edges are kind of like, how do I get from one, or the vertex is now, how do I get from one edge onto the next edge? And then I can again apply it on the edges. Okay, so PageRank is another scoring measure that we could use here that will again give a different way of chopping this up from the top down. All right, so again, like we talked about with clustering, there were a lot of these different methods here that we can use depending on the distance measure we use for clustering. It's kind of based on the importance score we assign to an edge or like a vertex here. Okay. All right, the other big thing I wanted to talk about before we talk about so communities is a way of scoring so there's a score called modularity, which is kind of probably the most famous score for assigning how well tightly knit is going to be a how well formed is a community, right? So this is going to be a score of how well formed is a community. The larger the better. Okay, and so you will typically give this, the modularity will be a score C, and I will say where C is a subset of the vertices. So a community, this would be a community, and I'll typically give it a score. I'll label it as Q. Okay, and this is nice in that in most senses, if you talk to most people, not everyone, they'll say that this does not have any parameters. So I can try and find communities that optimizes modularity without having to say I want K clusters. I don't need to set K. Or if I'm doing density-based clustering, I need to set kind of that radius and the kind of the density parameter. Modularity doesn't really have any parameters, although people have managed to put parameters back into it. Okay, but it's a score, and I just want to find the community that optimizes the score. So I want to find the subset of vertices that maximizes the score, right? The larger, the better. Okay, and so informally, the modularity of a subset are going to be the fraction of the edges in kind of the subset of the graph restricted to this community minus the expected number of edges in C. Okay, so I need to figure out, like, how do I define these concepts? Okay, the fraction of edges. Okay, this I can do as use the adjacency matrix. A, and this will be, and it's where Aij equals 1 if and only if the edge kind of ij is in E. Okay, so if the edge exists, then it's 1. And so then I can set the fraction of edges in here, okay, to be this term, be 1 over the number of edges divided by all the potential write this over here. Frac of edges for C. This is going to be equal to 1 over the number of edges times ij inside this community, Aij. That's going to be this term. Okay, and then the expected number of edges. This again, like I did for the clustering coefficient, is going to be normalized by the degree. Okay, so the expected number of edges, I will say the expected ij is going to be the degree of node j times the degree of node I divided by 2 times the number of edges. The 2 is there because we're dealing with undirected graphs, and so an edge could appear in the degree of either of these, the vertices. Okay, so this is this value. And so then again, that means that Q of C is going to be 1 over E ij in C Aij minus the degree of I times the degree of J times 2 times the number of edges. Okay, so this would be the modularity. Okay, and so you can kind of you can kind of write this down as a probabilistic model where you say that, let's say that the fraction of edges I expect on the overall graph to follow like this random graph model, right? So I think that the probability of an edge is proportional to the degree distribution to the degrees of the product of the degrees of the 2 vertices, assuming I'm given that. That would be this. And then my actual observation is the actual number of edges inside of this community. Okay, and so if I think of this as a probability, the product of all the edges, then this would be a likelihood ratio of the likelihood divided by this, and then the log of that becomes the sum of this minus this term. So you could think of it as a negative log likelihood ratio of the probability of having an anomalous group of vertices that has this many edges. And then you're trying to find that group of vertices that has more edges than you would expect. Okay, so this value is always, I think, if we normalize it correctly, it's always going to be This is always a negative 0.5 to value 1. Okay, so this is, it's always between negative 0.5 and it's large if it's greater than 0.3 usually. So if it's greater than 0.3, you would say this is large, this is interesting community. How do you find the high modularity subsets in the graph? Well, this is more challenging. Okay, so now you have to search over communities. Spectral clustering is a good heuristic to start, but then searching for communities and large, dense subgraphs and graphs is kind of a hard computational challenge. Okay, and the algorithms are complicated and there's still active research on this sort of things for this notion of communities or other notions of communities based on kind of things like clustering coefficient and other methods like this. All right, so this is kind of a overview of communities. We'll have one more lecture on Wednesday. I'll talk about graph embeddings and probably some kind of ethical kind of questions a little bit about representing things as embeddings. We'll finish up the semester on that. Again, if you want to look at some example posters, there are a bunch down here in front. I brought them today, so you can come have a look to get ideas of what to make for your posters.